Hold two small balloons rubbed on your hair. Pull them close. They either snap together or push apart. Today we'll discover the law that explains exactly how strong that invisible push or pull is and how to calculate it. By the end of this lecture, you will be able to state Coulomb's law in both scalar and vector form. You will also calculate the magnitude and direction of the force between two-point charges. Furthermore, you'll explain attraction versus repulsion and use the superposition principle for multiple charges. Finally, you will solve two short numerical problems and one free charge problem. Coulomb's law tells us the electric force between two-point charges. In words, the force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Mathematically, in scalar form, it is expressed as F equals K times the absolute value of Q1 times Q2, all divided by R squared. Here, K is Coulomb's constant, approximately 8.99 times 10 to the power of 9 Newton meters squared per Coulomb squared. The direction of the force is crucial. If charges have the same sign, the force is repulsive. Conversely, if they have opposite signs, the force is attractive. Coulomb's law explains the electrostatic interaction between electrically charged particles, a fundamental concept in electromagnetism. This law was first published by French physicist Charles-Augustin de Coulomb in 1785, based on his experiments with the torsion balance. It states that the electrostatic force between two-point charges is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. The force always acts along the line joining the two charges, which are considered point charges. Coulomb's constant, K, can also be expressed as 1 divided by 4 pi epsilon naught, where epsilon naught is the permittivity of free space. This permittivity value is approximately 8.854 times 10 to the power of negative 12 coulombs squared per Newton meter squared. Remember, Coulomb's law applies to point charges, meaning the size of the charged objects is small compared to the distance between them. For charged spheres, the charge can be considered to be concentrated at the center of the sphere. Coulomb's law shares similarities with Newton's law of universal gravitation, as both are inverse square laws. However, a key difference is that gravitational forces are always attractive, pulling objects together. Electrostatic forces, on the other hand, can be either attractive or repulsive. Another significant distinction is that electrostatic forces are vastly stronger than gravitational forces. When dealing with multiple charges, we use the superposition principle. This principle states that the net force on a particular charge is the vector sum of the forces due to all other charges present. It allows us to calculate the total force by considering each pair of charges separately and then adding the forces as vectors. Let's look at some illustrative examples and numerical problems. Consider two-point charges, each positive 1.0 coulomb, separated by 1.0 meter. To calculate the repulsive force, we apply Coulomb's law. F equals K times 1 divided by 1 squared. This results in a repulsive force of 8.99 times 10 to the power of 9 newtons. Next, imagine charges of positive 3.37 microcoulombs and negative 8.21 microcoulombs, separated by an unknown distance. Given an attractive force of 0.0626 newtons, we need to find the separation distance. Rearranging Coulomb's law to solve for R, we get R equals the square root of K times the absolute value of Q1 times Q2, all divided by F. Substituting the values, we find the separation distance, R, to be approximately 0.064 meters. Now, let's tackle a three-charge problem. Three charges, Q1, Q2, and Q3, arranged in a straight line. We will calculate the net force on Q2 due to the other two charges, considering both attractive and repulsive forces. This involves calculating individual forces and then summing them vectorially. For example, a positive charge of 6 times 10 to the power of negative 6 coulombs is 0.040 meters from a second positive charge of 4 times 10 to the power of negative 6 coulombs. Calculating the force between these charges using F equals K times Q1 times Q2 divided by R squared. The resulting force is approximately 134.85 newtons, a significant repulsive force. Coulomb's law is a cornerstone of electrostatics, explaining the fundamental interactions that govern charged particles. Understanding this law is essential for comprehending everything from static electricity to the behavior of atoms and molecules. Keep practicing these concepts and calculations to master the principles of electrostatic force.